We'll sort this array in ascending order using 5, 1, 2, 8. Let's go pass by pass and see exactly what happens. We start at the beginning, compare 5 and 1. Because 5 is greater than 1 and we want ascending order, we swap them. We start again, but skip the last element since it's correct. Compare 1 and 4, they're fine. Next, compare 4 and 2. They're out of order, so we swap them. Then 4 and 5 are compared, but they're fine. No swap needed. After the second pass, 5 is also in its correct position, right before 8.
We started with 5, 1, 4, 2. After a few passes of comparing and swapping adjacent elements, we ended up with 5, 8 in ascending order. That's bubble sort in action.
Let's sort this array of numbers. Watch them bubble up into order. Smaller numbers drift to the left. And now it is perfectly sorted.
Let's learn bubble sort. Compare adjacent elements. Swap them if the left is greater than the right. Repeat until sorted.
Next, we compare 5 and 4. Again, 5 is bigger, so we swap. Notice how the 5 is slowly moving to the right. Now we compare 5 and 2. Same story. 5 is larger, so we swap. The big element keeps bubbling towards the end. Finally, we compare 5 and 8. Here, 5 is already less than 8, so they're in the correct order, and we do nothing. A common implementation uses two nested loops, an outer loop for passes and an inner loop for comparing adjacent elements.
The outer loop runs n1 times in the worst case. The inner loop goes from the start of the array to n1 I, because the last I elements are already sorted. We also use a swapped flag. If no swaps happen in a pass, we break early, which saves time when the array is already nearly sorted. First line, void bubble sort int arr int n. Let's break it down. Void means this function does not return any value. It will modify the array in place. Bubble sort is the name of the function. Inside the parentheses, we have two parameters. Int arr, this is the array we want to sort. Int n, this is the number of elements in the array. So this function says, hey, give me an integer array and its size, and I will sort it using bubble sort. For int I equals 0, I less than n1, I plus plus. Panda. This line starts our outer loop. For int I equals 0, I less than n1, I plus plus. Int I equals 0. We start the loop counter I at 0. I less than n1. The loop runs as long as I is less than n1. I plus plus after each pass. We increase I by 1. Why n1? Because if there are n elements, we need at most n1 passes to make sure everything is sorted. After each pass, one largest element moves to its correct position at the end, so we don't need to keep going forever. Bool swapped equals false. Panda. Inside the outer loop, we declare a Boolean variable. Bool swapped equals false. This variable keeps track of whether any swap happened during the current pass. If we make even one swap, it means the array was not fully sorted yet. If we make no swaps in an entire pass, it means the array is already sorted, and we can stop early. This small flag helps make bubbles sort a bit faster on nearly sorted arrays. Visual idea. Show a toggle switch labeled swapped starting as OFF. Bool swapped equals false. Panda. Inside the outer loop, we declare a Boolean variable. Bool swapped equals false. This variable keeps track of whether any swap happened during the current pass. If we make even one swap, it means the array was not fully sorted yet. If we make no swaps in an entire pass, it means the array is already sorted, and we can stop early. This small flag helps make bubbles sort a bit faster on nearly sorted arrays. Visual idea. Show a toggle switch labeled swapped starting as OFF. This inner loop is where we compare adjacent elements and decide whether to swap them. Int temp equals arr j. Arr j equals arr j plus 1. Arr j plus 1 equals temp. Panda. These three lines perform the swap. Int temp equals arr j. Store the value at arr j in a temporary variable temp so we don't lose it. ARR J equals ARR J plus 1. Move the value from the right position, ARR J plus 1, into the left position, ARR J. ARR J plus 1 equals temp. Put the original left value, stored in temp, into the right position. Worst case time complexity, O and superscript 2. This happens when the array is in reverse order and every comparison causes a swap. Geeks 4 geeks plus 3. Average case, O and superscript 2 as well. Geeks 4 geeks plus 1. Best case, O, N. If the array is already sorted and we break early because no swaps occur in the first pass, launch school plus 2. Space complexity, O, 1. Because bubble sort is an in-place algorithm, it only uses a small constant amount of extra memory for swapping.